Let's skip the recording.
Skip the recording.
Yeah, mine's working.
All right, time to settle down. Okay, so what I did was I created 6 questions and put it into one single tar file. So there's only one file to download in this case, and when you unzip it, it unzips into 6 individual folders, and each folder is its own question. Okay, so let's go ahead and get started. So I'm going to extract it to today's folder, so someone has to remind me to upload it at the end of the day or at the end of the class, so that we'll have everything included in today's uploaded folder. So I'll close this, switch back into a command prompt, and use that for this test, for the practice test. Are there any questions before we start the practice test? Yep.
What are the answers to the test?
I know the answer to the practice test.
I have 6. How many questions will be on the
I have 6 right here, because I want to make each one, a little bit. It's a little sampling thing, and also I want to kind of isolate, the concepts that I want to test. So this way I'm not rolling everything into one big pot, and if that one big question could not be answered, there's no point left. So I want to make it so that you can look at each question, and each one has kind of like a specific thing that I'm trying to test. And if you feel comfortable about that one, you just go ahead and make that one work. Yep.
Will all the questions be weighted equally?
I do not think they will all be weighted equally. I have not decided how to weight them first. But by the time of the exam, they will be weighted, and you know exactly how they are weighted before you start answering questions. Yep.
What will the multiplier be for this test?
Well, that's the thing. I am building in, a multiplier. In other words, I might give you, 6 questions, of which 4 or 5 is the baseline. So there's one extra credit question, so to speak. Okay, but I will not tell you which question is the extra credit question. It's just they will add up to more than 100%, and that's the bottom line.
So there would be 6 questions or
Yeah, around 6 questions, but to get 100%, you only like 4 or 5, depending on how I weight the questions, because some questions may be a little bit more difficult. So if you can get those done, you can get more points compared to the smaller or simpler questions. Yep.
Will you tell us beforehand whether we're looking for syntax, logic, or both types of errors?
I think in these cases, I will just be using a C subroutine, and you guys have to implement it in assembly.
Oh, okay.
Manually. By yourselves.
V-S.
In other words, your submission should reflect how well you can program and not how well the compiler can translate C code.
What's the difference?
What's the difference? I don't know. Maybe I'll just give the compiler an A, since there's no difference anyway. GCC gets an A+ in this class.
It does do a good job.
I think that'll be the way to do it. I'll just add a new student account to GCC. So anyone who use some other means to turn in your assignment, I'll just give all the credit to GCC. I think that's the way to do it. Okay, so let's go ahead and take a look at the questions. I refuse to say how difficult the questions are. So because my assessment is never accurate anyway. Okay, so every question starts with something like this. Every question will start with a main.c. So there's a particular format to all the questions. They all start with a main program, main.c. And I'll turn on syntax highlighting just because it does make it a little bit easier to read. So in this case, and every single program is going to have one subroutine inside the pound if def and pound end if, and that's the one that you have to implement. In this case, we have read num that you have to implement, and this would be one of the lower point value type because this one is actually very easy to do. Okay, because when you look at the subroutine, do you see any ampersand, asterisk, square brackets for indexing or anything along that line? I don't see any. So that means this one is actually super duper easy to implement, and therefore the point value for this question is going to be pretty low. I mean, it may be 1/3 of a, or maybe even 1/4 of a more difficult one. However, if you feel that this is an easy one to do, then you can just nab those points real easy, just like that, to basically to make sure that you will start with at least some points. Yep.
Attendance?
Attendance. I can't really do anything about attendance at this point. I cannot drop people anymore. Maybe what I should do is, before the last day to drop people, I'll just drop a whole bunch of people, and then depending on whether they have continuing attendance, I will determine whether to reinstate them or not.
That would be a great policy for other classes on the campus.
Why? Are they the same way?
Well, in a way, like all the physics classes fill up, and then they drop out by halfway through the semester. Half the kids are gone.
Uh-huh.
Then someone who was following along with someone else inside the class could get in. That would be nice.
Ah.
But that's just me.
Yeah, well, and then there's the priority of signing up for classes. I think for most of you, is it opened up yet or not?
Yes.
Already
It's
over
already not for me.
Already
Not for you.
enrolled and being administratively dropped from classes.
Okay, because I know some classes are completely full and closed before some people actually have a chance to even try to enroll.
That's
in
how it is
class.
for me every time.
You can't even get onto the wait list in some cases. You can't even get onto the wait list, which is ridiculous.
I got this 3, and then I
All right. So for this particular subroutine, let's go ahead and see how we can implement it in assembly. Now, in every single question, I already give you a stub assembly file. So all you have to do is to specify the content of that file. Okay. And one thing you might want to do is to have your own templates so that you can copy and paste, a lot of the stuff that is going to be common to all of the assembly subroutines. Okay. I'm not going to say, how to do it. You guys have to kind of decide how you want to do the template thing so that you can copy and paste, a good portion of the code. You can do it in VI. VI actually is easy to do because you can do a read, which is basically, pound include inside the editor, and you can just include the content of another file into this file, which makes, the template thing, really, really easy to implement. But in this class, since, I can type fast enough anyway, so I'm just going to retype everything. OEPP is 0. Return address is OEPP plus 4. And in this case, I have 2 parameters. So it's a good idea to either copy and paste it or just flip back and forth. In this case, we have string as the first and pint as the second. Okay, so we'll go ahead and say string is the first one, which is right after return address. And then we have pint, which is the last parameter. So that's str plus 4. If I switch back to the C code, I do not even need any local variables in this case. The only statement in this one is to call scanf. Okay. Now, for those of you who don't know C, plain C, because in C++ you don't use scanf, you use the cin, and then you use the is it the greater than operator?
Less than.
Less than?
Yeah.
No, it's greater than to input something into
You
a
point the arrows
variable.
toward the variable that reads something
Right,
in.
exactly. So it's greater than. But do you care? It's a subroutine call, but do you really care, what scanf is actually doing?
Nope.
Nope. We're just, pushing the same parameters on the stack and call scanf. Whatever scanf returns, we'll return that too. So in other words, read num is nothing more than a relay to scanf. That's it. Okay. So how are we going to do this one? This is going to be pretty easy. Okay. So if I want to do everything by the book, I'm going to push EBP first to save the value of EBP. At the end of the program, I have to pop EBP back, and after this, I have to move ESP to EBP to save to set up the frame pointer. At the end, I move it back into ESP to restore the stack pointer. So my code, should go here. Well, what do you do when you have to call a subroutine?
You have to push the parameters on the stack in reverse order.
In a reverse order. So in this case, I'm pushing the last parameter first. So I have to push pint first. And in this case, I'm not pushing the address of pint. I am pushing the parameter pint itself on the stack. So we can do it with just one single push. And then the other one is the same thing. We just push it on the stack. Then we call scanf. Then we adjust the stack, which is somewhat optional. Okay, so we can adjust the stack here. And but what about the return value? What am I going to do with the return value?
Move it. Actually, you don't have to do anything.
The return is already the return.
All right. Yeah.
Yeah.
Move it.
Because it was returned in EAX already, and as far as I'm concerned, for me to return a value, I have to put it into EAX. So technically speaking, it is moving EAX into EAX, but this instruction is useless. It's pointless. It's not harmful. It is not wrong. It is just totally useless. Okay? So you might as well not have that instruction. Yep.
Why not play games with the calling function and dereference it in the process or something? Even though you don't need to, just to fuck with the caller.
Yeah, well, but that's the answer of this question. Okay, so this is a really easy one. I think it's a good warm-up type of question. It's not going to carry a lot of points, but it does have some points, for people who want to just, take on, as many questions as possible. This would be an easy one to take on and just, get some points. Unless I put restrictions on the kind of instructions you can use.
Oh, please let us use push and pop, please.
For instance, exactly, if I do not allow any push and pop instructions, then you will have to go through all the trouble to use, add and, move L and all that stuff.
We're good, thank you.
But for something like this, that would increase the point value of this question, which may not be a bad thing, because, if you want to replace push and pop with those other instructions, for the most part, it's just, search and replace, with a certain pattern. So those are easy points to get to. Yep.
How would we do this one if we could only push and never pop, and wanted to just pop everything except, or just pass our current stack on as the call to the next function without inserting our return address and other stuff into there? Could we do that?
In this case, yes, you can. You can just do a JMP to scanf, and it will do exactly the same thing.
Would you care to show us?
Sure. The alternative solution to this one. Now, this is a very special case, because it doesn't apply in most cases. In this case, we can do just that. Okay, because remember, the parameters are already pushed. And what I want to return is exactly what scanf is returning to me. So as a result, for this very specific case, jumping to scanf would accomplish exactly the same thing.
Well, that was really easy points right there.
But I kind of hesitated to say that, because I'm pretty sure in the final exam, the question will look similar to this one. It seems like the same trick would work, but it won't.
Can you move the screen over so we can see the original code too?
Sure.
Is it just underneath?
It's in the other tab.
Oh, it's on the other tab. Sorry.
You mean here?
I just want to see. Oh, it's reaching. Okay.
That's all it is.
I think there's a way to open up like two files, side by side, and have it split vertically. Is it dash uppercase O or lowercase o? It's one of those. Okay, so are we okay with this one?
Yes.
Okay. Now it's the same thing with your homework assignment. If you say make main, it is the one that uses your assembly implementation. If you say make main C, it is the one that uses the C implementation. So now you can compare the behavior of your program versus the other one. So if I say /main, it's going to read a number and it prints exactly the same number out. If I say /main, excuse me, I should have said /main C. This time it is just /, and it's the same thing. So the behavior of both implementations are exactly the same in this case. So are we doing okay with question number 1? Okay. So this one is, you should consider this one as kind of like a warm-up question, because it really does not exercise anything that is difficult in this one.
Will there be partial credit for this question?
No.
Okay.
It's good to ask anyway, right?
I mean, do we get a half point for just, typing something into the line? It could be gibberish, but do we get half credit?
You get negative.
Oh, I see.
Negative points. Because you wasted my time.
That's something like that. Negative points if it's not the right.
Oh, okay. The other thing is you can make tar too. Make tar will basically create, the tar file. So in this case, make tar will create this file.
So we'll be uploading 6 or however many files?
Well, it depends on how you guys want to do it. I can just make one single tar file at the very end, or each question can have its own tar file.
One tar file.
One big tar file.
No
So
difference to me.
well, that means one mess up. There's nothing for me to grade.
Yeah.
6 tar files, using 6 upgrades, 6 uploads means it's a little bit more troublesome, but you can upload something as soon as you're done with that one, and not have to worry about that later. Yep.
So you're saying these questions are independent from one another?
They are all independent. Yes, they have no, other than they may share some similar concepts. They are completely independent.
Okay.
Yep.
Will you be giving extra credit for the most innovative segfault?
I like that question.
Like one that will wipe my hard drive first before the seg faults.
Let's try copying a infinity to memory location -1. Let's do it.
There's no such thing as infinity when everything is mod 2 to the power of 32. Okay, so that's question number 1. Let's move on to question number 2. So question number 2, if you see that there's a whole bunch of files already here, you can say make it clean, and that will make it clean again. Okay, it will delete all the files that can be regenerated. So make clean will remove the .o files, the .inc file, and so on and so forth. So this one is a little bit more involved, because the one that you have to implement is this subroutine here. It's still not too bad. Okay, it is still not too bad. It's the question is, how do you get to a buffer that is pointed to by, pn, which is our parameter. And this part here, you also have to kind of figure out how to do it. It's one of those constructs that we talked about a long time ago. It's just that we really don't have any use for that until now. Okay, so shall we go ahead and try to implement this? Okay. The first thing you want to do is to look at the structure itself, which is defined in q2.h. So let's go ahead and take a look at q2.h, which will also answer one of the questions that some of you may have, because you did not catch what I said in the previous class about the homework assignment. It has to do with this type here, in32_t, which is in32, which is a 32-bit integer. I think last class, I already kind of mentioned something like this, of why there's a type like this and where it is defined. It is defined in standard int.h. You can locate that just by looking at the main.c, which has that include file already, and that's pretty much it. But in this case, I can put the #include inside this include file. It doesn't do any harm. It's it can be #included multiple times. So in this case, each node has I, buffer, and j, and every time you see something like this, I should be able to change and add or swap the order of the members, and your program or your part of the program should continue to work. Yep.
Would our program continue to work if you change the size of the buffer? Or is it required to?
It should. If I change the size of buffer, if you do everything else correctly, I should be able to change buffer, and your program should continue to work. Because your program should utilize, okay, if you look at a makefile, okay, I'm hoping that most of you at least understand the makefile. If you don't know how to make one, it's not a big deal, but if I give you one, you should understand what it is. So in this case, if you look at this makefile, there's a specific file called q2.inc, which is an include file in assembly. And that is generated by running node struct and capturing the output into q2.inc, which is basically what we have been talking about in the class, and also something that you have to do for the current homework assignment. So let me show you what I mean by that. If you go to C structs in assembly language programming, and I think it's section 4.2?
Yeah.
Oh no, it's a 2.2, 2.3. No,
2.2.
2.2. Okay, I messed up. Okay, so there you go. So basically, you have to do something like this in node struct in this case. So we'll go ahead and do exactly the same thing. Because I give you node struct already, I give you a stub, C program in this case, and you just have to kind of copy and paste it. I will give you something that looks exactly like this. Okay, it is going to be completely blank, with just the minimal features for it to compile. Now, since most of you or all of you, in here, know that I will be asking questions like this, you can just go ahead and create the necessary template, so that when you see a question like this, you just copy a file that is a template and just change whatever you need to change to make it work.
So we basically copy what we did for this assignment.
Exactly. It's the concept is exactly the same.
I got a quick question.
Yep.
When the file prints out, it prints out one string. Does it matter? I just put breaks in there just so it looked.
You have to. Oh, I mean, you have to insert the /n.
Yeah, that's
so
what I did. But does it matter if you don't?
If you don't, I don't think the assembler will take it. That's the
okay. I saw it and I was like, oh, that's not. I don't think that'll work.
I don't think the assembler will take it. So there's a /n that is missing in these particular ones.
That's what I figured.
And because I did not have the cheating file to the template to include here, I'm just going to recopy everything, which is not a big deal. Okay. This is a macro. Did your C class talk about macros like this type or not?
No.
Briefly.
Briefly. It's basically just text expansion. So every time you see uppercase offset with a parameter m, it will expand to the other side. That's basically what it is. It's just text expansion, and it's a very handy feature, but it can also be abused, and it can also cause problems if you don't use it correctly. So in this case, we have print, and this is something that you have to customize, because depending on the name of the type. In this case, if I look at q2.h, the name of my type is node, so it is probably a good idea to make this match the name of the type or the struct that we are defining. And so node has what? Node has I, j, and buffer. Okay. So we have I equals %d. So remember to have a /n at the end to give you a new line. And then we have offset. In this case, just I, like that. Now, if you want to make this even more automated, you can actually have another pound define, another macro, to deal with the entire line of printf. So in that case, the only thing you have to specify is just I, and the rest will just be taken care of automatically. I'm not sure whether it's worthwhile to make a macro like that. I'm just going to do it somewhat semi-manually or semi-automatically. And then we have J here. Just replace that with J.
You don't have to define the structure.
Oh, you have to define the structure up here. So it just says struct, in this case node, and obj, like that. And I think that should be it.
What about size?
The size.
Oh, the size too. The size is just the size of obj. So I can go ahead and just type make, and take a look at q2.inc, and in this case q2.inc has all the, seems like those are all the correct constants. Okay, are there any questions at this point? So this is what you have to do. Okay, even though some of you can hand calculate everything, but your code has to be correct even if I change the structure, add additional members, or move current members around. Your code still has to work. If you do it this way, as long as I don't delete members that are already here, your code should not be impacted whatsoever, as long as you use these symbol names. Are we doing okay so far with the explanation? Okay. So doing this is actually helping out with your homework assignment as well, because your homework assignment also has all these components.
But we did all this. I said, but we finished our assignment.
Some of you. Okay, so the next thing we want to do is to actually go ahead and implement the function that we have to implement, which is called simply called f here. This is also not very difficult. This one is actually fairly simple to implement. We're just doing a printf with pn points to buffer. So we'll go ahead and let me figure out how to do this side by side, so I can show you both the C code and the assembly code at the same time. I think it's uppercase -O, open and Windows side by side. There we go. Okay, so we can do a vim-o and then give it two file names. Main.c is one, f.uppercase s is the other one. So there we go. All right, so now we have C code on one side, and I'm going to implement the assembly code on the other side. So once again, you don't really have to do it exactly the same way that I do here, which is just repeating the same thing over and over again. In this case, there's only one parameter, which is pn. Pn is the only item after return address. I don't have any local variables, so that's pretty much the definition of all the labels that I need. But I also need to make sure there's a pound include q2.inc here, because that's how I get all the definitions related to node into here. Okay. All right. So now we are ready to implement the actual function. So once again, this is all boilerplate thing. Basically you can just have a template subroutine or template file, just copy and paste it here, so that you don't have to worry about this part here. So I'm doing a lot of stuff that can be completely streamlined and can be done like within a split second, but I'm doing it all manually anyway. All right. So this is the only part that I have to do, which is pushing the parameters, and and I don't even care about the return value of printf in this case. Okay, how am I going to push the buffer, the address of buffer that pn is pointing to, or the member buffer of the structure that pn points to on the stack? That's the question. Okay. Well, let's not do all the tricks that like pushing something and then do all the calculations on the stack. Let's do all the calculations in, let's say, EAX, which is one of the registers that we know for sure can be trashed. Okay, so we know that pn is important. Okay, pn is a pointer to a structure, so that is the base or the beginning part of the entire structure. So we know that is important. So one thing that we can do first is simply to say, let's copy the parameter into EAX first. If you prefer, you can write some comments here and say EAX has the address of the structure. Okay, so now we know the beginning of the entire structure. I just want to get to the address of the member called buffer. How do I do that?
You could just push buffer, or you can add.
I can add, I can add a constant to EAX. So that will be node underscore buffer, which is defined as the number of bytes between the beginning of this member and the beginning of the entire node structure. So adding this to EAX means that EAX will be the address of that member. So put some comments here and say EAX is the address of the buffer member. Okay, and that's exactly what I need to push on the stack. So I just say push L EAX. That takes care of the first parameter. The second parameter, that takes care of the second parameter. Now we can move on to the first parameter, which is %s \n. Well, how do you?
Will we just push a new line character?
There are several ways to do it. One way to do it is just to go here and then say format string, and define format string to be .asciz, which means that it's going to be null terminated, because all C strings are null terminated. Did your C class talk about how a string is null terminated in? Okay. So now we can just do exactly the same thing. You can type %s. Now if you're not sure whether \n is the escape character for ASCII code 10, you don't have to do it. Okay, you don't have to put your \n here. What you can do is simply to say the next line is .byte10. Because in assembly, when you do something like this, the reservation and the initialization of the bytes, it won't be the same with it, because the other one is null terminated already. So you have to do something like this. Do a .byte10 and then .byte0. So that will make it a null terminated string that has the %s and then a line feed character and then a null terminator. Just a long way to spell out what we usually spell out easily in C.
So
Yep.
why didn't the way you had the C on there? Why doesn't that work?
Because then the S would be null terminated.
Right.
The
Oh,
line
but you
character
need a
would
new
not.
line. Okay.
Yeah, because I want the new line not to be after the null terminator. It has to be before the null terminator.
So why can't you do the ASCIZ with the %s \n?
I do not know whether the escape character trick works in this case or not. It might work, it might not work. You can debug it. Then figure out whether it works or not. But this way, I know it works for sure. You can also look up the ASCII code of % and lowercase s, individually, and just have a longer, dot byte sequence, and that will work as well. Okay. Any questions about this one? Now, I did not switch to dots data. Do you think that's going to be okay? I'm not changing it, so it is okay for this string to be in code space and not in data space. Okay? So now I just have to push that parameter to, which is the first parameter. And when you push this, it is push $, $FMT str, not FMT str without the $. Because we are pushing the address, we are not pushing the content on the stack. Are we doing okay so far? Okay. Then we just call printf, and then we adjust the stack. And that should be it. Okay. So let's go ahead and see if this works or not. Okay. Make Q2 is working.
Oh, that's what it does?
Yep. Well,
If it was all so obvious.
well, what it does is
I like that. I don't know why, but I like that.
Could you put that on the final survey?
because what it does is it's just copying a particular literal string into the buffer member of the structure n or the node n, and then it calls f, which is just printing that particular member on the screen. Yep.
So if we did this program on the actual final, and rather than implementing all the C stuff, we just had it put out Q2 is working.
Well, your program is going to be graded by linking your assembly code to another, main program. So it will be tested, differently compared to, the actual main program here. But it still has to be implemented correctly. Okay. Any questions? So this is just one way to test, whether it's working or not. Any other questions? So let me show you the other things that I would do in order to grade your exam, because what I will do is I will change q2.h. So what I will do is to change q2.h by moving buffer into here and possibly adding some other stuff, like int 64t x here. Okay. So I will change, the structure of node, but making sure that buffer is still there and it still has at least the same length as before. If I do this and I say make main, it should automatically, you really need to take a look at these commands here to understand how it works. The first thing it recompiled was node struct.c, which is not a part of your program. Okay, this is really just a tool to generate the offsets into individual members of a structure. So that one got recompiled first and relinked and create the executable that we call node struct. And then the next thing that happened is node struct is called or is run, and the output is captured into q2.inc. In other words, q2.inc is now updated as soon as I update q2.h. The assembly version of the same thing gets updated as well. And then your assembly code is recompiled, and then it gets relinked with the main program. So in this case, if I type /main, it doesn't work anymore. Now what am I missing?
Q2 is not working because the G is missing.
So buffer is at 16. Node size is 48.
Hey, Professor Jack.
Yep.
What's G factorial?
G factorial. It's G times. Let's see.
H times I.
Yeah.
No, it's the other way.
It's the other way around.
F E D C B A.
Yeah.
But will it loop back around to Z? Is the alphabet where it reaches Z and then goes back to A, or is it terminated at Z?
Okay, now it's not working.
I'll let you
something here.
So we get extra credit if you can't even solve it?
I don't think your offsets are right unless the C program moved components around.
Well, this one.
This buffer should be at the very
Oh,
end.
I know what is wrong. I know it's a problem with my makefile because main does not get recompiled. That's it. Okay, let me show you all the commands, all the things that got recompiled.
Can you make it clean and then do it?
Yeah, if you make clean, then do it again. It will work.
Well, do it.
You have a clean target now?
Hmm?
Yeah,
If I
it
may
said
have a
that.
clean target?
There's a clean target. Okay. If you look at these commands here, did main.c get recompiled?
No.
It does not get recompiled. Does it need to be recompiled?
Yes.
It should be recompiled because it depends on q2.h. So this is a fault of the makefile because the makefile does not specify that main.o depends on not just main.c, which is implied, but it also depends on q2.h.
I believe it depends on main.o, not main.c, not main.o.
All right. Yeah. Otherwise, it's circular. So if I do it again, this time it did recompile main. The first thing is recompile main. So let's go ahead and this time it should work. There we go. So it's good to know, how, if you miss something in the makefile, what kind of stuff will happen, how will it fail? Yep.
If it's missing in the makefile for the test, will we get extra credit from?
No, because in your case you're not changing q2.h, so you're not exposed to that risk.
On the test, would we have been able to make clean?
You can just make clean. If you say make clean and then make again, it will force recompile everything.
Or not.
Hmm?
Clean has a problem.
If clean has a problem, yes, but clean does not have a problem. So are there any questions about Q2? No. Excuse me. Let's move on to Q3. So this time I can make clean first. Let's not do that. Let's take a look at that. You can actually quite easily tell which subroutine you have to implement. In this case, it is mult item. You have to implement it in assembly. So that is in C. And some of you know, said, oh no, because you saw item struct, which means this is also another question that has structure in it. Okay, so let's take a look at main.c, and then I'll open up another window. We can make this one wider so we can accommodate a little bit more width. And the other one is mult item.s, uppercase. There we go. And turn on syntax highlighting. So the subroutine that you have to implement is this one here. So this one is a little bit more messy because you have to return a struct item, not a pointer, but an actual struct item. So you have to return an entire structure in this case. It is also the first time that we see in this class that we are passing the structures by value, not by pointer anymore. Okay. Now it looks it looks really bad, but it really is not. Okay, because we already know the size of each item, of each struct item, so it's not really that bad. This one has got multiplication, inside here, and so on and so forth. But if you look at the structure of this line and the structure of this line, they are very similar. They're not exactly the same, but they're very similar. As soon as you figure out how to do this part, you just copy and paste it and deal with this part. Make sure you add the results of those two together. Once you know how to do this part here, you just copy and paste it and modify it so that you can just you just have to change the references to the individual members. The addition has to become a subtraction, and that's it. Okay. In other words, it looks really nasty, and the program is going to be a little bit long, a little bit lengthy, but it has a lot of repetition. There's a certain pattern to it. Okay. Are there any questions about this one? Nope. Okay. All right. So the first thing we have to do is not really to work on the assembly code. Okay. The first thing we have to do is to take a look at item struct.c, which is the program that we need in order to create all the offsets. So basically the same thing as last time. Yep.
How are you switching between sides?
Control W and then L to go to one side and H to go to the other side. I have to look at the keyboard because I just do it, but I don't know which key I'm pressing.
Oh wow, that's faith in your keyboard.
All right, so this is what we need to do first, but this time since I have Q2 that has something similar to this already done, so what I can do is I can look at Q2 node stub.c, and I'll just go ahead and copy and paste a bunch of stuff from here. What about we just...
You can take everything.
Just take everything.
Yeah, just about everything. Uh-oh.
Turns that part.
Well, it won't matter, that function will never get called.
All right, so I just copy and paste a bunch of items, but this time instead of node, we have item. So I just do a global replace of that stuff. And this is actually easier because item only has I and R.
I too.
I and R. Make sure this one is also updated. And that's it, I think. Should not have closed that. Okay, there we go. All right, so now that we have a C program to generate the offsets into everything, it is time to actually go back into the assembly code and try to figure out how to write it in assembly. Yep.
I believe in your .c file you're still including q2.h.
Oh, okay. Did I copy that part too? Well, it's okay. We can just let the compiler complain and then we'll fix it at that time.
Okay.
All right. Because our focus is really not that part. Those are easy problems to spot, because if you don't have a q2.h and you try to include q2.h, the compiler will just complain, and it's an easy problem to spot and an easy problem to fix. So what is not so easy is how do we do pass by value in this case? So OEBP is 0, return address is old EBP plus 4, and now we have the first parameter. The beginning of the first parameter is easy to figure out because it is just return address plus 4. The plus 4 has to do with the size of return address itself being 4 bytes long. So that means in this case, X is RET_ADDR plus 4. That's the easy part. Y is a little bit harder because where is Y relative to X? It has to do with the size, exactly. So this one is X plus, in this case, item underscore size. Now this item underscore size has to do with the size of X. It is not the size of Y. They just turn out to be the same. But in this case, I have to say X plus item size because X has a size of item size. Is that okay? Because it is very important to identify when we're adding a displacement to a particular label, why are we using that value? Okay. Is everybody comfortable with the concept of passing by value versus passing by reference? Okay. You guys understand the differences between the two? Okay.
Why do we not have a return value address for the first parameter?
That's also correct. We need that one first, don't we? So return value address is return address plus 4, and then this one is return value address plus 4. Very good. Now this is also the other reason why I used a reference only to the previous item, because now I just need to fix one item, and everything after that also get automatically adjusted. Okay, are we doing okay so far? Because we are returning a structure, and that's why we need a return value address in this case. I also know that in this case, the last instruction should be return $4 because we have to deallocate the 4 bytes for the return value address. That's just the convention, that we do things, for when we return a structure itself. Are we doing okay so far with this? This is going to be a little bit longer, but as I said, once you figure out how to do one part, the other parts are fairly easy. Yep.
Why is it return 4 again?
Huh?
I just missed what you said when you said return.
Because we have to, the callee, the subroutine, is responsible to deallocate the return value address itself. That's just the convention. That's what the C subroutine is expecting. So that's why you have to do it, because otherwise the C subroutine would get confused. The stack is out of balance. It is also written. This is also described in the notes. Okay, so in this case, it is entirely up to you to determine whether to use answer or not. Okay, why did I say that answer as a local variable is completely optional in this case? Exactly, because you can do everything to the return value area that is already reserved. So it's entirely up to you to decide whether you want to do everything to the local variable answer and then copy that whole thing to the return value area that is already reserved on the stack. So I would just save myself one step and do everything directly to the unnamed space that is allocated for the return value in this case. Okay? So this is not doing exactly what the C code is doing, but it is doing equivalent to what the C code is doing. Sorry? It is much more efficient to do it the way I'm doing it. I do not know. I don't know whether the compiler does that kind of optimization. Now, regardless, I still have to do something like this, and also that. So this is the stuff that I have to do anyway. So now in between here, I can now start to implement everything. Okay, I have to do the calculations first. Okay, so the first question is, how do I get to x dot I? X is a parameter. It is a structure passed by value. How do I get to the I member of a structure that is passed by value?
X plus item underscore I.
And then the whole thing using the base operand.
Yeah, parentheses EVP.
Yep. So we just move, in this case, x plus item underscore the name of the member itself, EVP. We have to move this one into EAX because EAX is one of the registers that mol is expecting. And then the other one is R of Y, so we can just go ahead and do a mol. Y plus item underscore R in this case, EVP. And after the multiplication, EAX is what I need to continue with the rest. So now I need a place to put that. Okay, I need a place to save the result of this multiplication because the result of the next multiplication has to be added to this one.
Let's push it.
Pushing is the easiest way to do it. If you move it into EBX, you have to save the content of EBX because EBX cannot be changed. EBX has to be preserved as far as the caller is concerned. So you might as well just push the result of this calculation on the stack so that you can use it later on. So the next one is x plus item underscore R EBP into EAX. I'm retyping everything. If you guys are good with your editor, you can just you can copy and paste really quick in this case. Just change a few items. After the multiplication, I have the result of the second product in EAX. So now how do I add the result of the second multiplication to the result of the first multiplication?
Add what's stored at ASP into. Oh, that works too.
Or the other way around. I mean, this works too. But you have to remember that we have one extra item on the stack right now, okay? Because we have the finished product on the stack right now, okay? The other way around is it works too, okay? If you flip the order, the question is where do you want to put the entire result? If I do it this way, then the result is in EAX at this point. Okay, which is actually better because it is very handy. I can now I'm ready to put it back into answer.I, which in this case I'm putting it into the area that is already reserved by the caller for the return value. Are we doing okay so far with this?
You still have to clean up the stack though?
I still have to clean up the stack, yes. Yes, I still have to clean up the stack. Now, actually, come to think about it, I'll probably do it the other way. Okay. I'm just thinking ahead a little bit because I will still need EAX to calculate where I'm supposed to put this stuff here. Let me ask you this question. If I move return value address EBP into EAX. What is EAX after this instruction?
The address of the return value.
So it's actually the address of a struct item.
Yes.
Okay, very good. So how do I store something into the I member of that particular structure?
You can just do your offsets
Okay, I can do the offset.
with the base address in front.
Okay,
You could move L what ESP is pointing to what is it, answer,
what about something like this?
or I component of, yeah, that.
That is nifty,
Yeah, it's even easier.
very nifty. Okay, now let's take a look at this instruction, because I'm not, you don't have to write code, like this, because I know it is combining a few items into one single operation, but you need to at least understand what this instruction is doing, okay? Because you have to keep track of what kind of stuff is on the stack at this point, and also, what is in EAX and what this, operand is about. Okay, so let's start with, let me display the line number so I can refer to the line numbers. So, line number. Okay, so let's start with line 19 first, okay? Is everybody convinced that at the end or after line 19, I will have the sum of the products saved on the stack? Okay, so that part is okay. I will have both your products calculated and the sum of those two products stored on the stack at that point. So I'm just stashing it away so that I can use it later, because I don't want. I know that I need EAX for something else later. Line 21 is moving the return value address from the stack, copying that into EAX. So as a result, after line 21, EAX is the address of a struct item that is already reserved on the stack as the return value. Is that part okay? So EAX is already pointing at the beginning of a struct item. The operand of line 22, item underscore I, open paren EAX close paren, is going to be the member I of that particular struct item. And it is also automatically dereferenced because it is a based operand. So the question is, what am I doing to it? Well, I'm taking whatever the stack pointer points to, which is the sum of the two of the products, and just put it into this location right away. So I'm saving the answer, directly into the area already reserved for the return value. Is that part okay? I just have a nagging, uneasy feeling that I may not be recording the audio. Oh, it is. Yeah. Well, but everything is visual also. I mean, there's the code, displayed on the screen. It's just.
You gotta understand it.
But it'll sit there for 2 minutes and we'll go, what does he say?
There's not enough visual comments.
Okay, so here comes the easy part. The second statement, which is this statement here in C.
Is the opposite of all that.
Exactly. So it's line 13 to line 23. Line 13 to 23, copy to here. Great. Now I cannot remember which part is which part. Okay. All right, so let's do that again. That's the problem of copying and pasting when everything kind of looks about the same. So we say line 13 to line 23, copy to here. There we go. Okay, so that's better. Okay, so what we need to do in the second one is, there are a few differences here that are very important. The first thing is, this is a subtraction. It is not an addition. Now, when you have a subtraction, not an addition, it is no longer commutative. So you got to make sure that you have the calculations done in the right order. Okay? So let's just go ahead and try this one first. This one I have not really actually thought about it. So I'll do the R times R first. Oh, by the way, this is wrong. So if this is wrong here, you have to make it wrong too, just to make sure that your code is consistent with this code here. Because I'm not assuming everybody knows, complex numbers. So you have to make your code consistent with the C code. That's the very important part. Okay. So we push the product onto the stack first, and then we do the second one. The second one is both referring to the I component. And this time we have to be careful because we don't want to add that to whatever is already on the stack. Okay, and in fact, this makes me want to reverse the operation so that I can keep whatever is saved on the stack the actual result. Because right now, I have to change this one to a subtract long instruction. But when you are doing a subtract long instruction, you're subtracting the second operand from the first operand and then storing the result. Excuse me, you're subtracting the first operand from the second operand, which is actually the correct order in this case. So this is all done correctly. Okay. Is everybody convinced that the subtraction subtracts the first operand from the second operand? It is, in this case, we are saying, whatever stack pointer points to minus EAX, and the result is now stored back into whatever the stack pointer points to, which is exactly what we want in this case. Okay. And then we have to change this one to, the R member, and that's it. There's no mem copy at the end. Why don't I need to do a mem copy? Don't we have to do that all the time when we have to return a structure? I'm doing everything directly to the area already reserved for the return value. So there's nothing to copy back after this. Okay. Is that okay so far? Yep.
Is that because you pass by value?
No, it has to do with I am doing all the calculations and storing the result directly into the return value area that is reserved by the caller. Okay. So unless I make some stupid mistakes here, which I think I have one mistake that I haven't fixed yet in the C code. So let's go ahead and make it go bad. Make clean. Make. No, there's no mistake.
Except for the x.r, x.r.
So this part is right. Yeah, but that part is consistent with C code.
Yeah.
So let's make main C. Run the C code first. Okay, it reports I equals -4, R is 1, and now we run the other one, which uses the assembly code, and it reports back the same value. Questions? No? Okay, just.
I was just noticing that you built the program sometime in the future.
Oh yeah. Time travel is nothing. I mean, that's how I can come up with these answers. I just travel in time to the forward. I would travel to the time when I actually have the solution already figured out, and then bring that solution back now so that I can discuss that solution, so that I will know the solution again in the future.
That's quite a little loop you got going on there.
Well, the nice part about that is I really did not really have to think to come up with a solution. I just have to bring that solution back from the future. Yep.
Isn't that amount of time travel conveniently the difference from GMT to our local offset?
Yeah, the Earth has to rotate. What can I do about that? All right, so this is question number 4. Okay, does everybody understand the solution of question number 3? The details can be a little bit tricky, so what you need to do, is to study that and just, add your own comments on each and every line, at least the tricky one, so that you understand the solution. Okay, that's a very important step that you have to do. So here's question number 4, and we'll do the same thing. We'll look at the C code and we'll look at the assembly code. In this case, you can see this one does not have any structure, so that's an easier question. Okay, this is what we need to implement in assembly. It looks really ugly, because we have a dereference followed by a post increment and then followed by another dereference. So this is a test to see whether you can still remember what auto increment is about in C. Do you guys understand what is auto increment?
I don't know what auto increment is.
Well, that's post increment.
One
Yeah.
is to itself.
And this one also, there's also another trick here. Now the other trick is PPI is a pointer to a 64-bit integer. So you have to pay attention to the type. Okay? So are we doing okay so far? With all the things that you have to pay attention to? Okay? All right. So now this time, we don't have to deal with the structure, so we can start right away with the assembly code. Okay, old EBP is 0, return address is old EBP plus 4. Yep.
Wait, are we dereferencing one of the pointers, incrementing that, and then dereferencing it again after?
Well, we'll go ahead and figure out how to do this. Okay. The trick to do this kind of thing is do it step by step and leave enough comments so that you know what EAX is or whatever register you want to use is at any particular time.
But isn't that incrementing a pointer?
It is incrementing a pointer. Yes, it is.
Okay.
How much pointer stuff did you guys cover in your C class?
If we say none, will you move this question off the final?
Sorry?
If we say none, will you move this question off the final?
No. Because now you know what it means. I will explain exactly what it means. This is only one single instruction, but we'll talk about it. Okay. It's just like with any type of thing. Okay, if you encounter, okay, let me just give you an example here, which is entirely trivial. Okay, if you see, a calculation like this, okay, I will use variables in this case, a times b plus d plus e, and then the whole thing divided by f, and this whole thing plus g. Okay, if you see something like this, which calculation do you do first? Do you do the division by f? No, you have to handle d plus e first because it is embedded deepest. It is nested deepest within the parentheses structure. It's the same way with this code here. Okay, you just have to deal with whatever is embedded deepest first, and then you work your way out to figure out what you have to do. Okay. All right. So let's go ahead and try to tackle this one. Just one step at a time, and we'll deal with it like that. The first thing is we know that we have to deal with PPI. Okay. Since we know that we have to dereference PPI, it makes sense that I have to copy that parameter into a register, because I cannot dereference unless something is already in the register. Then I can use the indirect operand in order to dereference something. Okay. So the first thing I will do is I will move PPI EBP into a register. I will pick EAX because EAX is something that does not need to be preserved. Then I will write a comment here and just say that EAX is PPI after this instruction. Does that make sense so far? Okay. So the next thing we want to do is to dereference PPI, but I don't want to do any dereferencing just yet because of the post increment operator. Okay. Now what does post increment do? I'm just going to add the comment here so that we can talk about it. If I say, let me give you a sequence of instructions here, and you tell me what is the value of j in this case. So I equals 4. This is an initialization. It is pseudo C code. I'm not really dealing with the semicolon and whatnot. Okay. So if I say that j equals I plus plus, what is the value of j after the second assignment statement? 4. It is 4. It is the value of I before it is incremented. But after that line, I becomes 5. Okay? So that's the whole concept of post incrementing. Is basically you are incrementing whatever you're incrementing, but for the outside world, you're using the value of before the incrementing. Okay? All right. So how does that relate to what we are doing here? So that means this second dereference is using the value of PPI before, or it's using whatever PPI points to before it is incremented. Are we doing okay so far?
But it's outside the parentheses, that doesn't matter.
Well, it is outside the parentheses, and that's exactly why this whole thing returns the value of whatever PPI points to before the auto increment. It's just like here, if I put parentheses, okay, let me show you exactly what I mean by that. Putting parentheses around this one does not make any difference. Because I++ as a whole thing returns the value of I before the increment. Okay. So what I need to do now is, I know that I need whatever PPI points to, and I need to use that later on. So I'm going to push it first. Okay, I will push whatever EAX points to, which is what I need later on to dereference again. Okay, I'm pushing it on the stack. Now I can go ahead and actually change whatever PPI points to and do the increment of that thing. Okay. How much should I add? Okay, I know this has to do with an add out instruction, and what are the two operands of this add out instruction? In other words, how am I actually going to implement the increment part? I save the value of whatever I'm incrementing to be used later on, so that part is okay. I saved that already. Yep.
$4.
$4. 8.
It's a pointer.
64.
It's
You
a
are
pointer,
correct.
and the
This is
architecture is 32-bit, so 4.
no.
The width of a pointer. You're incrementing it by the size of a pointer, which is 4.
Okay, I am incrementing this thing here. What is that thing?
That's a pointer.
That's a pointer to
A pointer.
no. Okay, this is a pointer to a pointer. This is a pointer to a in64.
Okay.
So you have to increment by 8 bytes in this case. Let me say that again. This is a pointer to a 8-byte thing, right?
Why would the...
This is a pointer to an 8-byte thing. So you are incrementing a pointer to an 8-byte thing, and therefore you have to add 8 to that pointer. No? Not convinced?
Maybe. I say try it and see.
Okay? So this is what you need to do, is to increment 8 or add 8 to whatever PPI points to. And that will finish up, that gets the increment part done already. Okay, so I'm done with the increment part. And then what I have left here is, a pop out instruction. And I'm popping back this whole thing into EAX so that I have EAX. So the question now is, what is EAX? Okay, I'm pushing, this is literally pushing whatever PPI points to, okay, the old value of whatever PPI points to, and I am basically popping back, so EAX is old whatever PPI points to. And what am I supposed to do with that again, with this assignment statement? To initialize that to 0, okay? All right, well, we can do that. Move L. Tell me what I'm supposed to do here. $0 to indirect EAX, okay? Because whatever I push back is whatever PPI points to, and what does PPI point to?
64.
No, PPI points to a pointer that points to a 8-byte integer. Okay, so EAX is a pointer at this point, so I have to dereference it. But I'm not done yet. Because what is EAX pointing to? What is the size of one thing that EAX points to at this point? It's an 8-byte thing. It's a 64-bit integer. So I need another move L instruction here to take care of the most significant 4 bytes of that thing as well. And that completes the operation. Are we doing okay so far? No?
I think what you did was implement a prefix or a pre-increment.
A what?
You added 8 to, you incremented the pointer, and then you made it 0 rather than making it 0 and then incrementing it. I think you did it in reverse order.
Okay, let's find out what we are doing. Let's comment out every single line. Let's comment each and every single line. We are, okay.
Let's use the debugger and check the results.
1 back in the EAX. Now he's making the next item 0, not the current item.
Okay, this one here is incrementing whatever PPI points to, right? So at this point, whatever PPI points to is already changed. It's modified.
Yeah, so that, but we're trying to make the current item 0, not the next item.
But that's why I'm popping EAX back from what I saved earlier.
So then but as soon as you do that dereference again, you're now accessing the item you already incremented.
No, it's not. Because what I saved earlier is whatever PPI points to already. And PPI, whatever PPI points to is changed by this instruction. But when I pop it back, I'm popping back the value before I added 8 to it. So I'm actually working with the value of whatever PPI points to before the increment.
Okay, I see.
So that's why the post this operation is actually going to work correctly. We know that there will be 2 dereferencing or 2 indirect operand in this case, because you can see in here there's 1 dereference here and there's 1 dereference here. So we know that we need to do a indirect twice on EAX, which is actually done here. The first time is here, and then the second time is here. Okay. Any questions about this one?
So we have to copy that back into PPI.
It's already done. Whatever PPI points to is already changed by this instruction. So the increment is done here, but this makes me it makes it possible to use the value of whatever PPI points to before the increment. Yep.
When did you store the incrementation of PPI back into PPI?
Right here. I'm not incrementing PPI. PPI was never changed. It is whatever PPI points to that got changed. It is whatever PPI points to that got changed. If you look at how this is used, how the subroutine is used, I am passing the address of PI, and PI is a pointer to a 64-bit integer to the subroutine.
Let's run it and see how it works.
That's exactly.
We're initializing your array for you.
Okay. Make clean. Make. Hey. I made clean already. Apparently, it's not deleting everything that I should delete. Okay, let's see. Make clean. What else is here? Make file itself. Okay, touch everything. If you cannot make it work, brute force it.
I guess your files like being touched.
Okay. Well, first of all, I have to make sure that the program doesn't do anything. Okay, because this one it does not show it. But first of all, I have to make sure my program does not crash. Because if it is not done correctly, this one could easily crash because I will be using the dereferencing incorrectly. So instead of using an address as an address, I can use an integer as an address. So it can easily crash in this case. So the question now is, how am I going to how am I going to test this program to make sure that it works?
Well, you can increase your for statement to print out the last item.
How about we use a mem set first to set the whole array with something first, okay, with something other than 0, right? So we'll just initialize the whole thing with. Now I cannot remember how to use mem set, so we'll say mem set. Okay, the destination, the constant, and how many. Okay. So the destination in this case is the entire array. The content is FF, and I have to do it size of R many bytes.
But you need to use an int, right? This said to use an int, right?
Int? What?
Yes, the type was int.
0xFF is an int.
Very small int.
Yeah, it's an int. And then we can print out the whole thing here. So we can say for I equals 0, I is less than 32, plus plus I. Now we have to print out the value of a 64-bit integer, which is a long for this compiler. And this is something that you don't have to deal with. This is just that will print it out. And in this case, we're printing R bracket I. Okay, so this will be short. Okay, so we can say make main C. So look at the C implementation first. Okay, fine. I have to pound include string.h first. It prints a whole bunch of zeros, which is good. Okay. Now,
32 zeros.
now just to be sure that it should not be doing that. Right after the mem set, we'll just do the printing before the mem set, and then do it again after the mem set. And also, let's make it so that we don't have to deal with that many things. So let's just shrink it to 4 items in the array. Right?
We can print out 32.
Hmm?
On the fall, you write that I and 32.
Oh, did I use a constant 10?
Yeah, just try it and see if it works.
Should have used a const or a macro here.
Time to find.
Yeah.
See, that's why you use constants.
There we go.
When we go back to day 2 of the 360 class, use constants.
Okay, so that's good because FF, a whole bunch of FFs makes -1. So it's printing -1 before I call the subroutine, and then after we come back from the subroutine or the loop that calls the subroutine, everything became 0. So the question is main going to do the same thing? Because that's what we're testing. And it does. So now the question is, what if we made a mistake? Okay?
We'll try to access location 0 if we make a mistake.
Well, let's make a mistake. Let's make a very subtle mistake. Like, okay, forgetting that this is we're dealing with 64-bit. Let's say that we forgot these are 64-bit numbers, and these are 32-bit numbers instead. Okay, so let's make that mistake. In what is the main of this subroutine in inc.s? Yep.
How much partial credit would we get if we forgot we were working in assembly and did it in C instead?
Okay, so that would be the mistake that I make. I'm making these 2 changes here so that I'm pretending that I'm making a mistake, not realizing that I'm dealing with 64-bit numbers and assuming these are only 32-bit numbers. Okay, so this would be the kind of mistake that someone can make in this process. And the numbers will look like this. Because it will only get to the first 2 items, and then the other 2 items would not be touched. Now, the other thing that people can do is only remember about the 64-bit number 1/2 of the time and not the other half of the time. So to do that means, I will do something like this, and then the other half is not fixed. So what do you think will happen this time?
That's me right there.
Okay? So I'm incrementing the pointer by 8 every single time.
So every other number is going to be -1.
No. These will all become huge numbers because I'm only initializing the least significant 32-bit numbers. So everything will become a large negative value in this case. Because the most significant 32 bits are still FFs. There's still a bunch of Fs. Only the least significant 32 bits are initialized to zeros. So let's see, what is the symptom of this program? Because I want to show you guys, the symptom so that when you encounter problems like this, you know what it means. Okay? So are there any questions about this?
This is a really small number.
So I'm going to fix everything so that it works again, so that you have a correct solution to start with, to study. Yep.
Did you remember to save all your wrong versions and properly tag get branches for us? So we can
Yes,
get
it
them
is
all
saved
out?
in the video capture.
Yeah.
That's a fun way to save. Okay, let's take a look at question number 5. I don't think we
Question
have enough.
number 5.
Number 5 is alive. I want a remake of Short Circuit.
Yeah.
Yeah, that would be awesome.
And this one does not have any structures either. Okay, now this one is actually quite interesting because we are trying to implement string and compare using assembly code. Okay.
Implement or
What if we don't even
call?
before we try to implement it? Can we know what it does?
String and compare? It compares up to n characters if you give it two strings.
I see. Okay.
And it has to make a conclusion based on, if you run out of characters to compare, it will just give you the result of the last comparison. If if the two strings start to differ before you run out of characters, then it will just show you that result instead. Okay. And the only part that is a little bit tricky here is this last part here, the return instruction. In your C class, did you guys talk about the this operator, the question mark and the colon?
Yeah.
Does anyone want to help me explain this?
No.
The first
No?
one or the second one.
This is a condition. If the condition is true, this is returned. If the condition is false, this entire thing is returned. But if you look at this entire thing, it is exactly the same thing. So that means this is a multi-branch conditional statement. That's basically what it is. If this is true, return this. Else, if this is true, return this. Else, return this.
That's a nifty way of sticking an else if into a return statement.
And you can put it on the same line too. It looks good on the same line.
But does it look good on a resume if you do that?
It depends on who's interviewing. Okay, so do you guys want to talk about this one? I mean, we are running out of time.
No.
No?
Well, what's question 6?
Question number 6? Let's take a look at 6.
That's a really good idea.
If they make a new short circuit movie, number 6 has got to be the evil one, right? I mean, because of the number 6.
Yeah.
Yeah.
No, it has to be number 666.
Now, just number 6, they just have to make another, number 5 and paint it, matte black and just call it number 6 with red LEDs for eyes instead of blue LEDs.
Yeah. Now I'm gonna go home and watch Short Circuit. Thank you.
Okay, so this time, we
no,
do
it's
have a
an
structure.
array.
Yeah, it's an array of structures. Okay.
Oh.
Holy cow.
No. Don't
It's
worry
easy
about
enough
it.
to do. We've all done it before.
Don't worry.
Don't worry.
Okay, don't worry about it. But this is the subroutine that you have to implement in assembly. Okay, it has a loop. The loop part should not bother you. Okay, the loop part really should not bother you. So since we don't really have time and I don't want to drag this on too much, I will just go ahead and tackle the part that is the most complicated one. Okay. In other words, I will assume that you know how to print out, the offset to each member of a structure. So I'm not going to spend time to deal with that part. Yep.
Can you record the video and post it? So, yeah.
It won't be the same because you guys cannot ask questions in that process.
It'll be
But it's
better than
better
staring
if
at
you
that.
explain
It's
it.
better than that.
Yeah.
Explain the whole thing?
Yes.
I can explain the whole thing, but I do want to kind of at least go over line, let me see.
Is it the array next equals the address of the array?
Yeah, this line, line 13 is the most difficult line. So once again, to some people, this is the unlucky number.
Yeah.
You planned that, didn't you?
Well, I mean, that takes a lot of planning ahead of time to make it coincide with the line 13. And next, I have a test, on this Friday too. Some students, decided we don't want to come to, we don't want to take any final exam on a Friday on a Friday the 13th. And I said, I'll just be very nice and be very religion neutral. I'll find out all the unlucky numbers of all the religion and make sure all those numbers are used in every single question. So I'm very sensitive. Yes.
Equal opportunity discrimination.
Exactly. I do not discriminate. Actually, I do, because some people can say that. But what about the atheists? They won't be affected by all these numbers, because they don't believe in anything.
That's not true. We don't not believe in anything. We're just not afraid of it.
Okay, so let's deal with this one. Okay, this is the only one that is a little bit tricky. Everything else, I think we know how to handle already. Okay, so it's an assignment statement. So how do you tackle an assignment statement? Which side do you deal with first?
The right side.
The right-hand side first. Okay, so let's deal with the right-hand side first. The right-hand side is, we want to take the address of a particular element of the array. The index is I plus 1. Okay? Now let's not make any assumptions about I, that it is actually just incrementing all the time. So we actually have to do the calculation. So the first thing we have to do is to do something like this. So we have to move I EBP into, say, EAX, and then just go ahead and add $1 to EAX, because that becomes, okay, if I want to comment here, EAX equals I plus 1. Is that okay? Okay, now that we have I plus 1, we have to calculate the displacement or the distance of this element from the beginning of the entire array. That means we need what? Multiplication, right? We just need to multiply the size of each element by the index that we are using inside the square brackets. So now we can just do a mul, and that constant is already defined, assuming the other part of the program is already done. So that would be, let's see, what is big underscore size. Okay. Now, if you cannot do this, you just have to put it into a register and then do that later. Okay. So now we have EAX being the number of bytes from the beginning of the entire array to the element that we want to access. But where is the array? This is just from the beginning of the array to the element that we want to access. But this doesn't tell me where the array is. So what do we have to do to EAX to figure out the actual address of the element itself?
We have to add it to
The labor style.
yeah, your whatever your
Array.
yeah, that.
Something like that?
Yeah.
Okay. So now after this, EAX is the address of element array bracket I plus 1. This is my right-hand side. I'm done with the calculation of my right-hand side. Okay, so since I really don't know what else I have to do, I'll just go ahead and push it on the stack first. Okay, in other words, I want to do some calculations using I on the other side too. So I'm going to push this one on the stack so that I can use that later. Okay, what about the left-hand side? The left-hand side needs to calculate the address of P next of element I of the array. Okay? Well, but that's really not that much different from the calculation that we just went through. It just has one little extra step to go to the member that we call P next. Okay? And that's really quite easy to do. So what we have to do now is to do about the same thing. We have to move I EBP into EAX. And now there's a way to do this to shortcut this, but I'm not going to do the shortcut. Okay, the shortcut way is to realize that EAX is pretty close to the left-hand side already. Okay, they're only off by one element. Okay, but I'm not going to use that trick. I'm just redoing everything by the book. So I'm putting I into EAX and then do the multiplication to the size of each element in the array. I add the base of the entire array to the offset to that particular element. So in this case, at this point, EAX is the address of element array bracket I. Are we doing okay so far with this? Okay. And I think we can make this screen a little bit bigger by just getting rid of this side here. There we go. Okay. But I'm not quite done yet, because what I want to store the right-hand side to is not array bracket I, but a particular member of that structure. Now, since I'm already at the beginning of a structure, how do I take it back. I already have the address of the beginning of a structure. I need to get to the address of a particular member of that structure. What do I need to do?
Offset.
I just need to add an offset. Okay. Now, I can do all that stuff, Should I use a long way and then a short way to do it?
Just pop it.
Yeah, I can just pop it. Because I already have the right-hand side on the stack right now. So any pop operation will retrieve the right-hand side and put it into whatever operand I specified for the pop out instruction. I already have EAX being the address of a structure. I just need to get to a particular member of that structure. So one shortcut way to do this is to pop into big underscore p next, open paren EAX. That's the shortcut way to do it. Okay, that's a really, really quick way to do it. Is that okay?
It will be okay.
It will be okay. But but this is the solution. This will work. It's just a matter of okay. But this makes it a good study material because you really need to understand why this will work. Okay, and that makes for really good study material because it has elements of the stack. It has a whole bunch of calculation to get to the address of an element in an array. It also has the calculation of, okay, I know the base of the entire structure. I just need to get to the address of a member of that structure. So it has all those elements. And remember, all those elements are actually in your current homework assignment as well. So understanding this kind of stuff, I think is going to be beneficial not only for the final exam, but also for your current homework assignment.
The next 26 hours?
Can you show us the long way too, real quick? You say
The long way? Okay, sure.
just comment that out or whatever.
Well, it's already comment in C.
Whatever.
I can double comment, I
Thank
guess.
you.
Okay. So if you want to do it the long way, one way to do it is to say add L, $big underscore P next to EAX. So now EAX is the address of member P next of array bracket I. Okay. And if you want to avoid popping into the final place to put it all together, then one way to do it is to pop it into say EDX, okay, and then we have to move L EDX, which is our right hand side, to the destination, which we have already calculated to be EAX. So that's the long way of doing it. The short way of doing it is just one pop out instruction. Yep.
Don't you have to save EDX then though?
No, because we have been modifying EDX all day long, and it has not been causing problems. Remember, div L and mol, they both modify EDX implicitly, and that's not an issue. I think I think it doesn't cause any problems because if you have to return a 64-bit integer, it uses EAX and EDX to return a 8-byte integer, and that's why EDX is assumed to be modified as well.
So
But
EBX and ECX are the special ones.
So don't.
EBX, and I would save and restore the registers anyway. In case if you have doubt, EAX for sure can be modified. But everything else, if you have any doubt and don't want to deal with whether it is the case or not, just save and restore the registers.
You're safe and sorry.
Yep. But this instruction, using a pop-out instruction, does not use any registers at all. So that also makes this a really good solution because it pops directly into the destination without the use of any temporary registers. Okay, so that's it for today. This is our last lecture. Yep.
Did you say you were going to go and do a full video of question 5 and question 6?
I will go ahead and do that.
That would be great.
Yep. But then there won't be any questions from you guys, so it's still better than not having anything. Okay, I'll do that.
We'll put the questions in the comments section on the YouTube video.
I will also do a video on the solution of the homework assignment, but I cannot do that now. I will do it tomorrow.
Tomorrow, like 7 p.m.
7 p.m.
That gives me about 5 hours to make sure I get it done.
I'll make it fun. I'll make it 11:50.
Oh, come on.
You have 5 minutes to watch and type at the same time.
So
that
next
would be so
Tuesday,
cool.
8 p.m. in the lab.
Yep.